Hello and welcome back to High Peak Education. I want to thank you for staying with me through all these lectures. And now I want to perform another lecture. This will be a somewhat brief one, also on electromagnetic induction, but of mostly two applications, electric generators and electric transformers. So these are both applications where we use Faraday's law. So let's jump into here. Let's first discuss electric generators. What are these electric generators? So notice that an electric generator is similar to an electric motor, except the input is mechanical energy and the output is electrical energy. That's kind of the opposite of an electric motor. An electric motor had input was electric energy and the output was mechanical energy. So it's just sort of the opposite. Now, notice that electric generators utilize the fact that by rotating a coil in a strong magnetic field, an EMF is induced. Note that because of brushes, or what we call a commutator, the current generated is alternating current, which is very often abbreviated AC. Notice, remember, that magnetic flux, we discussed this in the previous lecture, is BA cosine of phi, but lowercase phi is the smallest angle between the magnetic field and the area vector, and that phi is often deemed as omega t. You can think of omega as the angular rotation rate, or really it's also going to be the same thing as the angular frequency. It's really more or less just the same thing. Now, by the way, typical commercial generators use water flowing through a dam, or wind turning a propeller, or turbines spun by expanding steam, etc., to turn much larger coils. Okay? So what we have here shown is a loop in a strong magnetic field, and look, these are slip rings, and these slip rings are attached to the armature of this loop, and here's an external circuit, and look at these brushes. These brushes allow for the current to be flipped over, that is alternated at every half turn. And then here is the equation for the EMF generated by an electric generator. It's NBA omega sine omega t. So notice that it's the number of turns or coils, magnetic field strength, area of a loop, times angular velocity, same thing as angular frequency, times sine of omega t. This sine of omega t just bounces between 1 and -1 and just makes this EMF alternate in time. And by the way, if the EMF alternates in time, if there's any resistance, then the current should alternate in time. So we call this alternating current. So here's just an electric motor in its stripped down version versus an electric generator. Notice that here's some stationary contacts and a rotating loop and some input current. The output is rotational kinetic energy. That is to say, electric motor is often used for many things, like a drill or a fan or something. And again, the input is from a voltage or maybe like a DC power source. And these slip rings just allow you to have alternating currents every half turn. Notice with an electric generator, you have to put in mechanical input. So there has to be either a person turning a crank or some sort of, again, expanding steam or a waterfall or something, turning this crank. There will be magnetic forces that oppose the rotation. But when you push against those magnetic forces, especially at a constant rate of rotation, you'll produce a nearly constant magnitude AC circuit. But the actual AC will oscillate in time. When I say constant magnitude, I mean if it's converted to DC, it's nearly constant magnitude. But the output is electric energy when the input was rotational kinetic energy. So in practice, we don't often change the magnetic field strength or the area size of loops for Faraday's law. We often change the orientation of a coil. So here's an example of a real looking electric generator. Here's a generator inside a hydroelectric dam that uses electromagnetic induction to convert the mechanical energy of a spinning turbine into electric energy. So if there's water coming in here, you can imagine there's a very, very, very large turbine inside here where the water spins it. And again, I'm sure there's some sort of loop in here and then some sort of magnet, and we produce electric energy. And by the way, notice we have dozens and dozens of these electric generators, so we're producing a lot of electricity at our electric power plant. So let's briefly talk more about inducing currents due to proximity. Remember what Faraday's experiment was. A primary coil is connected to a switch and a battery. The wire is wrapped around an iron ring. So that's what's shown here. A secondary coil is also wrapped around the iron ring with no battery present in the secondary coil. That's what's shown here. And then here we have an ammeter. Second coil is not electrically connected to the primary coil, and we'll examine what the current produces from closing, leaving alone, or opening, or leaving the switch open. At the instant the switch is closed, the galvanometer, which again is very, very similar to an ammeter, needle deflects in one direction, then quickly returns to zero. When the switch is open, the galvanometer needle deflects to the opposite direction and then quickly returns to zero. It'll read zero when there's either steady current or no current in the primary circuit. That's because there's no changing magnetic field in time due to Faraday's law. So electric current is produced in the secondary coil due to a time-varying magnetic field in the primary coil. The induced current exists only for a short time while the magnetic field is changing. The existence of a magnetic field is not sufficient to produce an EMF. It must change in time. Remember, Faraday's law is, how does charge change with time? Okay, so basically what Faraday himself was discovering was a transformer. When he had two different numbers of turns on the primary versus the secondary, he was essentially discovering an electric transformer. Transformers convert one alternating current voltage into another. An example would be power lines that carry voltage at many kilovolts, but a transformer converts this into standard 120 volt AC. Again, at least in the United States, that's the standard voltage for alternating current. A standard transformer is either going to step up or step down the voltage. Now, a step-up transformer goes from a smaller voltage to a higher voltage. A step-down transformer goes from higher to lower voltage. This particular example is going to be a step-up transformer because we go from a smaller number of turns and a smaller voltage to a higher number of turns and a higher voltage. By the way, this is what the transformer symbol often looks like. Not really going to expect you to know that for the sake of this class. So again, P is primary and S is secondary for the coils. By the way, sometimes this is just called coil 1 and coil 2. Really means the same thing. Coils are wrapped around typically some sort of iron core. Now, by the way, that iron core is a ferromagnetic material. The idea is that we can generate a stronger magnetic field through that ferromagnetic material as a result of induction. Okay? So, if the input voltage is AC, then we get a changing magnetic field from one coil to the next. And then finally, an EMF is induced in the S, or the secondary coil. So let's have a look briefly at the transformer equations. So Faraday's law of induction can be used to find the output voltage. Okay? So let's let the primary coil have NP turns, or what's shown here, N1. And let's let the secondary coil have N2 turns, or NS turns. Interestingly enough, Faraday's law is going to tell us that voltage in the primary divided by number of turns in the primary equals voltage of the secondary divided by number of turns in the secondary. This is just a nice proportionality equation. So the mathematics are actually pretty straightforward here. Now, by the way, the conservation of energy, and it turns out energy per time is just power, dictates the ratio of the current in the coils. So if the power is conserved, now by the way, this is only true for an ideal transformer. Most real transformers have power losses due to transmission, due to inefficiencies, due to some energy being lost in air, due to friction, resistance, all kinds of things. But as long as the power is conserved, that's a very ideal transformer, very idealized, then power primary equals power secondary. But we recall that power is equal to voltage multiplied by current. So Vp Ip equals Vs Is. That is the multiplication of voltage and current on either the primary or the secondary is conserved. So let's have a brief look at some real electric transformers. What do these look like when you actually view them? So here's an example of maybe like a substation. This might be like, say, in a neighborhood. Notice there's some people here working on it. A substation takes the electric power, which is at many, many kilovolts, usually 15 kilovolts or something, and we step it down to a more manageable voltage. Now that voltage still might be 1,000 volts, 500 volts, something like that, but it's put out into the neighborhoods, and then these smaller transformers, which are near your neighborhoods, actually step it down even further to what's typically in your home, which is 120 volts. Now, by the way, some commercial or industrial places in the United States use 240 or 480 volts, but I digress. Here's an example of a transformer. Notice that we can put this coil through this very strong magnet. This is kind of an iron core. And notice here's some other transformers. Now, I will perform an example of a transformer's calculation. And I don't necessarily think it's the same as Optimus Prime joining us as far as transformers. But again, we have input, output, primary, secondary, coil 1, coil 2. So I want to thank you for watching this video. Please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. I look forward to reading your comments in the comments in this video. Please share this video amongst your social network if it would help them. And I will look forward to seeing you in the next video.